So this is the video recording for Pre-Calculus Unit 3, Lesson 3.5 on rational functions. So to give you the quickest of overviews, rational functions are used in things like satellites or other things that are possibly orbiting Earth, right? And it's part of this family of functions, and what we're going to do in this unit here is we're going to identify some key characteristics of that family of functions, be able to determine some things like their characteristics, the range, the domain, and then we're going to introduce ourselves to this thing called asymptotes and removable discontinuities, right? And we'll talk more about that later. So getting into it, 3.5, all right? So remembering that we can have horizontal and vertical lines. So again, our horizontal line being this red one here, where it's y equals b, and b is that y location. So maybe y equals 2, right? And you're gonna have a line along the y coordinate of 2. All right, and then vertical line here is where we have x equals some number, and that number is the x coordinate for that entire line. So again, this blue line right here. Okay. And if we're looking at these quick questions here, okay, it says a vertical line through the point 50, okay? Well, a vertical line is going up and down, so that's dealing with the x coordinate. So if we check at what the answer for that should be, it should be at x equals 5. All right, then a vertical line through -2, 1 would be at x equals -2. Dealing with horizontal lines, that's where we're talking about the y's. So that would be at y equals -7, and this one will be at y equals 4. All right. So then if we're looking at where we're going to use these, there's these things called rational functions. And simply it is when you divide two polynomials, right? It's the quotient of two polynomial functions. All right. And rational functions mean that it has a domain that is restricted, right? It's not continuous all the way through. So there is some restrictions. All right. Meaning there's a place where you're not going to have values. All right. And one of those things is where the denominator does not equal 0. Okay, so if the denominator equals 0, right, the bottom of our fraction equals 0, it forms this thing called a vertical asymptote. A vertical asymptote. All right, and we'll talk about what that looks like, but a vertical asymptote is a line in the graph of a function that cannot be crossed. All right, it gets really, really close to that vertical line, but it never actually touches it. All right. And then we can also have this thing called horizontal asymptotes. All right, a horizontal asymptote is a horizontal line, okay, where the graph of a function approaches can approach it, but the difference here between horizontal and vertical is that in horizontal asymptotes, they can actually be crossed, okay? They can actually be crossed, whereas a vertical asymptote, they never get crossed. But really what's important here is knowing where those are located and knowing what the end behavior of the graph looks like. Again, we focused a lot of our attention on that in the last unit. So still remembering it's what the end behavior looks like, and that is to say, you know, if x goes towards infinity, which is in the positive direction or to the right, and if x goes towards negative infinity or in the negative direction to the left. All right. So moving forward here, all right, finding different asymptotes. So if we're looking at this, all right, so a vertical asymptote in this first one here is the vertical line x equals 2. And you can see here that both of these graphs look like they're getting really, really close to 2, but they don't ever cross 2. So that would be the vertical asymptote here. And if we look for the vertical asymptote in this other graph here, we can see it's at x equals -3. Again, they get really, really close, but they never cross. And how did I know that it's going to be at x equals 2 or x equals 3? Because the vertical asymptote is what value of x is going to make the bottom here 0. So if I have 2 times something, what's going to be subtracted from 4 to give me 0? And the answer for that is 2, right? Because if I have 2 times 2, that's 4. Minus 4 gives me 0. I cannot divide anything by 0. So therefore, it's going to form this vertical asymptote, this line of, oh, nope, there's no answer for that. Same thing over here. If I've got -3 plus 3, doesn't matter what else is going on. I've got a 0 denominator, so I cannot have that. That is no longer true. All right, and the one that I find is a little bit more difficult, that we're going to go into more details here later, is this horizontal asymptote. All right, the horizontal asymptotes. So again, This one here is at y equals -1, and this one's here is at y equals 1/2. So again, it looks like they're getting really, really close. Maybe they're crossing, but they're definitely slowing down and getting really close to it. And so we're going to figure out as to how we could figure out what those horizontal asymptotes are. Again, in my opinion, they're a little bit more difficult, not as blatantly obvious as the vertical ones. All right, so if we practice finding our asymptotes here, all right, if we look at this first equation, okay, we're going to have a vertical asymptote at x equals 1, right? Because 1 minus 1 gives me 0, all right? If I look at the second one here, my vertical asymptote is going to be, it's 3x plus 3, right? So -1 is going to give me that value. Moving forward here, I've got it divided by x squared plus 1. So I don't actually have a vertical asymptote, all right? And I guess I can get rid of that horizontal one while I explain this. The reason I don't is because even if I have 0 squared is still going to get added to 1, right? And there is no square value, right? No real number that we can square and get a negative value that's going to get rid of this positive 1 there. So we actually have no vertical asymptote. In this one, our vertical asymptote here is at x equals -1. And then finally here, our vertical asymptote is at plus or minus 2. And again, the reason that is because our equation here is x squared. So either -2 squared is going to give me 4 or 2 squared is going to give me 4. And both of those answers are going to give me a 0 denominator. All right, now the one that's more difficult here is the vertical asymptote. So if I look here really, really closely, it looks like there's a line here at maybe x equals 1, maybe y equals 1 or y equals 2. If I click on my vertical line, it's at y equals 2, right? So both of those look like they're approaching, but they're not going to cross. All right, my horizontal asymptote here is at y equals 1/3. That's at y equals 1/3. All right, and again, it's what looks like it's going to cross, but it really doesn't. And we'll talk about how to find those later. All right, our horizontal asymptote for this guy here. All right, we can see that it's at y is equal to 3. It's y equals at 3. Again, that's where the graph seems to be flattening out, and that graph's not going to cross. And then in the last one here, we have a vertical asymptote between all 3 of these graphs here. Okay, so right there at y equals 1. Y equals 1. Again, we'll talk about how we calculate those. All right, but it's not just important knowing what the vertical or horizontal asymptotes is. The reason we want to do this is because we want to be able to figure out our range and our domain, right? So the values of our x values and what we could possibly get out for our y values, right? So again, domain being our input or our x values, right? It's like our independent variables that we input into our equation, all right? And then our outputs are the range. Okay, and we have 2 different types of domains now that we understand the basics. We have explicit and implied, right? And if it's explicit here, it means it is listed or described, like it's easily you can see it. All right, if it's an implied domain, it requires a bit more finesse here. All right, so it means it's implied for the function here. So for example here, if we have implied domains, it means that we don't really see it, but we know that it's going to follow the same trend versus explicit, right? Maybe we see it right there and it's very obvious or it's stated in a table, okay? And with rational functions, you got to be particularly concerned, again, about what makes the denominator equal to 0, right? We cannot have a 0 denominator. So any x value that's going to make it 0 is no longer part of our domain, right? We don't include those because if we tried, it would mess up the graph. So this is going to be important because we're going to say our x values are all of this, but the things that are going to make this not true, okay? And that's going to be for our x values. Now, determining the range here, as it says, can be a little bit more tricky. Okay, it can be a little bit more tricky. And this is where really utilizing your graphing calculator is going to come in handy, because if you utilize your graphing calculator, again, you can now see the shapes of graphs rather than trying to look at an equation or try to guess based on, you know, what information you're given. All right. Now, we'll watch this video here on finding the domain and range of a function, now knowing what we are looking for. Again, domain being x values and range being y.
To find the domain of this function, first consider values that will cause the expression to become undefined. You will do this by solving the equation 2x minus 4 equals 0 to yield x equals 2. Since you do not want x equals 2 to be plugged into the function, you can describe the domain as all real numbers except x equals 2.
Okay, so again, that's saying x can be, or our domain, x can be any number except for x equals 2, right? Any number will be fine, except for if you plug in 2, it's going to mess the whole equation up, right? So that's basically what that's saying.
For the range, consider the graph shown here. You can see there are positive y coordinates and negative ones too. There is even a y-coordinate of 0 at x equals negative 1. In fact, the only value that appears iffy is y equals 1 over 2. We can see whether the function will ever assume that value by attempting to solve the following equation.
All right, and pause there in case you didn't see it. What he figured out, it was y equals 1 over 2 because that looked where there was the horizontal asymptote, right? It looked like that's where the horizontal asymptote was. So then he plugged in for the y value, y equals 1 over 2, right? And then he went and tried to solve it. And when he tried to solve for x, he came up with the final equation 2 equals negative 4. And obviously we know that's not true. And he's going to explain what that means here.
There is no such x-coordinate that will make this function take on y equals 1 over 2 as a value. This means that the range will be stated as all real numbers except y equals 1 over 2.
So again, you can plug in any value for y and you're going to get an output of x except for at the location y equals 2.
Start with the domain by considering values that cause the expression to become undefined. Solve the equation x plus 3 equals 0 to yield x equals negative 3. Since we do not want x equals negative 3 to be plugged into the function, we can describe the domain as all real numbers except x equals negative 3. For the range, consider the graph shown here. You can see that there are positive x coordinates and negative ones too. There's even a y coordinate of 0 at x equals negative 5. In fact, the only value that appears iffy is y equals negative 1. Check to see whether the function will ever assume that value by solving the following equation. Because there is no x-coordinate that will make this function take on y equals negative 1 as a value, the range can be stated as all real numbers except y equals negative 1.
All right. So again, those are the highlights there, but looking more in depth into this, okay, can we find the domain and range ourselves? All right. So looking here for our domain, right? Again, that's any value that's going to make this denominator 0. So our domain for this one is any value except for x equals 1. All right, x equals 1. All right, and we'll come back to the range here in a second. But if we look here, okay, we can kind of see that it looks like there is a horizontal line at y equals 2, okay? So we would plug that in for y equals 2, solve it, and see if we get, and we don't get the value that we want. So this one would say, okay, all values except for where y is equal to 2. All right. For this next one here, for our domain, okay, it is any value except for x equals negative 1, because 3 times negative 1 plus 3 is going to give me 0. So any value but that. All right, looking at the range here, it is kind of more difficult to see, but the answer is going to be 1/3, anything but 1/3, and we'll talk more about how we know that coming back from slides. All right. For this one here, okay, so the domain is all real numbers because, again, there's nothing here that we talked about. There's nothing there that is going to make this one not true, okay? So that's all real numbers for our domain. X can be anything. All right, now, remember, we talked about having our horizontal asymptote at y equals 3. Okay, so for our range here, since we have no values less than 0 and no values greater than 3, we can say our range is 0 to 3. Or we say y is greater than or equal to 3 and less than 3. Sorry, greater than or equal than 0, and it is less than 3. All right. For the next one here, our domain is anything but -1, again, because -1 would make that 0. Our range here is a set of values, and we'll explore this a little bit more in the next couple of slides here. All right, and then the following one here, domain. Okay, our domain is anything but x is positive or -2, because that's what's going to make this 0. All right, and then our range is from y is greater than 1, or y has got to be less than or equal to -1, right? So this middle region here is we don't have any values. We don't have any values, okay? And we'll get into this thing here called oblique asymptotes, all right? So if we look at this following graph here, right, that was that kind of weird one. You may have noticed it didn't have a horizontal asymptote, okay? It doesn't have a horizontal asymptote, but there's a line that kind of mimics that. And if you look, it's kind of horizontal here, all right? And it looks like it's slanted, which is why we call this a slant asymptote or an oblique asymptote, all right? And to figure out the equation of this oblique asymptote, we could do our synthetic division that we worked on here. All right, and if we looked at x squared plus 4x plus 6, and we divide by the x plus 1, okay, we end up with x plus 3 plus 3x plus 1. All right, and what we find out here is our oblique asymptote is the quotient, all right, polymer without the remainder x plus 3. Okay, or it's without the remainder, so it's x plus 3. All right, so when we divide by this, we find out, hey, x plus 3 ends up being our oblique asymptote. So along this line here of x plus 3, we clearly have an asymptote. It's a linear line. All right, and the reason that we can kind of ignore this remainder here is because as x gets really, really, really large, so as x gets closer to infinity, all right, 3 divided by 1,000,000, or 3 divided by, if we go 3 divided by 11, okay, that's going to be a small number, but imagine 3 divided by 1,000, 3 divided by 1,000,000, right? Eventually, this is going to get so small that it's just going to act like 0, all right? So what we can say is that remainder drops out, and after we did our division here, we found out, again, there's a slant asymptote along the line of x plus 3, all right, along the line x plus 3, all right, and then there's one more interesting characteristic we need to take a look at, and it's this thing called removable discontinuities. All right, if I really look at what the definition they give us for that is, it's a location in the function's graph where the graph appears to be continuous, but it's not. It's also called a hole, right? So it's going to be a point along this line here, a point along this line where it's actually non-existent, right? So remember we talked about on our number lines, right? When we had our number lines, we said open holes did not include the points and closed holes did. So when we have a discontinuity, right, it's going to end up looking like a open hole on our graph. All right, so for example, if we look at this graph here, okay, x squared minus 4, all right, so we know that we definitely can't have x equal to 2, right? We definitely can't have x equal to 2 because 2 squared minus 4 is going to give us 0. So we have our line here at x equals 2, okay? But if we also notice, remember, this should also be x or negative x squared, because negative 2 times by -2 gives me positive 4. So technically there should be another line here. So the question is what the heck's happening, right? And what this is it's that removable discontinuity. So what this is actually going to look like here is at x equals -2, there's going to be a hole indicating, hey, this isn't included. All right, this isn't included. All right. And looking at the factors, okay, looking at the factors as well, we can tell that we have 2 vertical asymptotes, right? X plus 2 and x minus 2. All right, so those are our 2. Again, we can see the one here, but the second one we can't see, but what that means is that we have this discontinuity or this hole here. All right, and something I want to point out to you, okay, your graph or your graphing calculator may not show you these holes on your graph. Like most of the time they are not going to unless you're specifically plugging in for them. Okay, so this is where you've got to use that little bit of extra brain power. It's not just what I like to call plug and chug. You've got to use your brain power here. So again, you got to make sure you're paying attention to the fact that yes, I found the first one, obviously it's there, but you can't just use the graph. You've got to also look at the equation there. All right, and this is the slide that I think is really, really crucial. It wraps it all up for us, okay? So using algebra to determine these existence of our asymptotes for our different rational expressions, okay? So if we go down to vertical asymptotes and removable discontinuities, again, this is anything that's going to make that denominator 0, okay? So anything that's going to make that denominator 0. And for a removable discontinuity, all right, you can either do it one of two ways. You can look for what should have been a vertical asymptote on the graph but doesn't appear to show up, or what you can do is look for shared factors between the numerator and the denominator. All right, so for example, if we had x plus 2 on top and x plus 2 on bottom. So they were common factors, okay, but that still made a removable discontinuity. All right, and highlighting here, both of these values are restrictions or not included in the domain because it makes the function undefined, right? We can't calculate it. So that is not included when we're giving our domain values here. Okay, and this is the one that I really, really wanted to point out to you. Okay, this is the one how I knew some of the things earlier, and I'll go back to it for you. But horizontal and oblique asymptotes. Okay, so this is talking about looking at our equation. All right, so it says let m denote the degree of the numerator. All right, so the top part. So if I've got x squared on top, m would be 2. And n denote the degree of the denominator, so the bottom. Right, so this is saying if the top number is smaller than the bottom number, right? So if I've got x squared over x cubed, the horizontal asymptote is going to be at y equals 0. Okay, right off the bat, you just know that. Okay, it's going to be at y equals 0. All right. If they're the same, so if I've got x squared on top and x squared on bottom, the horizontal asymptote will be y equals b over a, where b is the coefficient on top and a is the coefficient on bottom. All right, and we'll do a couple examples with this one. All right, and then lastly here, if m is greater than n, okay, so if we've got cubed on top and squared on bottom, then the asymptote is going to be oblique. All right, so then we've got to find the quotient polynomial, which gives us our linear line equation. All right, so these are the 3 tricks for figuring out the horizontal asymptotes. All right, so if I go back to this practice here, all right, if we look at this, okay, if we look at number 2 here, all right, I've got x and x, right? They're both to the power of 1, so they're the same power. So this is the case where I take the top leading coefficient, so 1 divided by 3. So my asymptote here is going to be at y equals 1/3, right? It's going to be at y equals 1/3, so that guy actually works out. All right, looking at this one, it's squared and squared, so I take 3 divided by 1. So again, my horizontal asymptote is going to be at y equals 3. All right, now why this one, we have a greater number on top, so I've got 2 over 1. So because this is the one where I'm going to have that oblique. So this is where we had to find the linear line, right? And we ended up solving for our linear line here. Okay. And then the last thing I want to point out here is y equals, right? So we said that normally, right? Normally for this one, since the bottom exponent is higher, this should be at y equals 0. Okay, it should be at y equals 0. But we have this plus 2 here. So you treat this front part as if y equals 0, and then we would plus 2. So our horizontal asymptote's at y equals 2. Okay, if we had something like this and it was minus 5, our horizontal asymptote would then be at minus 5. Okay, so those are just a couple of examples here, really going through what it's telling you here with the horizontal and oblique asymptotes. All right, so putting it all together here again, this is where we can go through it a little bit more. All right, so finding all the vertical asymptotes. All right, so the vertical asymptote here for this guy, the vertical asymptote is going to be at -1/2, right? Because 2 times -1/2 plus 1, that's going to give me 0. All right, now my horizontal asymptote, since this is x to the first over x to the first, it's just going to be 1 divided by 2. So my horizontal asymptote is going to be at y equals 1/2. All right. Looking at my next function here. All right, looking at my next function here, I've got a polynomial expression on bottom, okay? I got a polynomial expression on bottom and a polynomial expression on top. So if I do the horizontal asymptote first, since I've got x squared over x squared, it's 2 over 2. My horizontal asymptote is going to be at 1. All right? Then my vertical asymptote is going to be at x equals 5. Because at x equals 5, that's what's going to make this denominator equal to 0. Okay? And then I also have this removable discontinuity at x equals -1/2. All right, and again, the reason that is because if I look at this, I've got x squared. I've got x squared. So I've got to be careful because at x equals -1/2, this is also going to make the bottom expression equal to 0. Okay, so it's going to make the bottom expression equal to 0. So if you see it on the graph at x equals -1/2, if we were to zoom in there, you should see a very open hole there. Okay, for the next one here, I've got an x squared on top and an x on bottom. So for my oblique asymptote, or my horizontal that turns oblique, what I had to do is I had to factor, right? And I have to find the vertical line that's left. And so when I take x plus 2 out of this top equation, I'm left with 2x minus 4. All right, and that's where my oblique asymptote is going to be at. All right, and then my vertical asymptote is no different. Okay, x plus 2, what's going to make that equal to 0? That's going to be -2 there. All right, so looking at the answers to our study guide here. Okay, so a vertical line through the point, right? We already went through all of these, but again, knowing the difference between vertical and horizontal and what that means in terms of graphing. So vertical lines, you're going to pull the x coordinates. Okay, horizontal lines, you're going to pull the y coordinates. All right, matching each term with its definition. So a rational function is a quotient of 2 polynomial functions. A vertical asymptote is a line that the graph of a function cannot cross. A horizontal asymptote here is a line that the graph of a function approaches, and it may cross it, but it's more likely that it's going to be approaching it forever and ever. All right, and then finally, D, the end behavior, is what happens as the graph approaches, either really far right, really far left. Okay, looking at these guys here, what are the asymptotes? So again, looking for either on the graph or on the expression or on both, you look for what's going to make the denominator 0. And then for this one, since they're both raised to the first power, you do 5 divided by 1. So that's how I get 10 and 5. Same thing here, okay, except nothing is going to make this expression untrue. But I've got x squared, so -4 divided by 1. So my answer for my horizontal is -4. All right, plenty of examples like that. Now, the value for the domains are sometimes called the inputs, while the values for the range are sometimes called the outputs, or domain is x, range is y. Sometimes the domain is stated explicitly, and other times it is implied, right? So like we're saying, going on forever and ever and ever. Okay, so again, here for the domain and range, so what you can just say is that x cannot equal 3. And again, it can't equal 3 because that's what's going to make this false on the bottom. All right. And the range is everything but where y is equal to 1/3, because again, these are the same degree on top and on bottom. So you divide 1 by 3, and that's where this is not going to be true anymore. All right, specifically looking at this next one here for the range. Okay, so I've got an x to the 0th power and an x to the 1st power. Okay, so normally this would be y equals x, but this is what we talked about, but it's got a plus 5 here. So y would equal 0 plus 5, right? Y equals 0 plus 5, because when you have a higher degree on the denominator, y is equal to 0. All right, looking at this one here, okay, x squared, so my domain is all real numbers, and my range goes from anything from 0 to 4. All right. So then looking here, this is talking about your oblique asymptotes. Okay, so an oblique asymptote is where you have something greater on top, right? And then you have to divide, and we use our new method here. Okay, when we divide by this, we end up with a linear line expression. So I've got x plus 1, right? Because we can ignore the remainder, because after a while it's going to go away forever and ever and ever. All right, and then a location on the function's graph where the graph appears continuous but is not is called a removable discontinuity or a hole. Okay, for what value of x might the graph of the function appear continuous while it's not, right? That would be 7 and negative 7. All right, 7 and negative 7. And then when you actually plug this in here, you're gonna find out that those would be considered, right, both of our vertical asymptotes here. All right, so we know that's going to be 7 or negative 7. Okay, in order to make sure that we can figure out which one's going to be the whole, right, we have to look for the same expression or the same factor on top and on bottom. So on top we have x minus 7, and on bottom we have x minus 7. So the value for which it might look continuous but it's not is going to be at x is equal to 7, right? So we can rule out the negative 7 because it doesn't have the same factor on the top there. All right, so then again, these are our super helpful rules for figuring out horizontal and slant asymptotes. Okay, so if m is less than n, then the horizontal asymptote will be y equals 0. Again, adding or subtracting whatever else you have at the end of the expression. If m is equal to n, then you're going to be b divided by a, right? B divided by a. And then if m is greater than n, it's going to be oblique, so you're going to follow that same process here that we just talked about.